Hi everyone, so this is chapter 11.5 of the Year 1 Statistics and Mechanics book on the constant acceleration formulae. This chapter is on variable acceleration, so you might be thinking, why are we looking at constant acceleration in the chapter of variable acceleration? The constant acceleration formulae are known as the Suvat equations. That's what most people would refer to them as, but I like to still call them the constant acceleration formulae because it reminds me that I should only use them in situations where I have constant acceleration. Now, earlier on in the book, we derived these 5 equations using a velocity time graph where we have a particle moving with constant acceleration with an initial speed of u, a final speed of v in time t. And to get one of our equations, we considered the gradient of this curve, and that gave us our acceleration. And then we looked at the area of the curve to get us our displacement. And then we do various things with those to get the other equations. So that is one way of deriving these equations, but we can also derive these equations using calculus. So example 8 illustrates how that's done. So example 8, and this is on page 191, says a particle moves in a straight line with constant acceleration a. Given that its initial velocity is u and its initial displacement is 0, prove that blah blah blah. So I'm just going to write down the information that they've given us. They've told us that the initial velocity, so v0, is equal to u, and they've told us the initial displacement is 0, so s0 equals 0, and it's moving with constant acceleration a. And we want to prove that its velocity v at time t is given by v equals u plus at. So we're deriving that really common equation, v equals u plus at. So the way we do that is we think to ourselves, well, velocity is the integral of acceleration with respect to time. We're trying to derive an equation for velocity, so we're going to integrate the acceleration. And remember from the information given in the question, acceleration is constant. This is just a number, 1, 2, 3, 4, 5, 0.5, whatever. It's just a number. So when we integrate that constant, we're going to get v equals at plus the constant of integration c. Then we're going to use the information given in the question that the initial velocity is u. So when t equals 0, v is u. So when t equals 0, so this term is 0, v is u. So the constant of integration is c. So from this, we can say that v equals u plus at. So we've derived that equation now using calculus. Part B, we have to derive its displacement s at a time t is given by s equals ut plus a half at squared, another equation that we use all of the time. So here we think to ourselves, well, the displacement, we can integrate velocity with respect to time. And we have just derived this equation here for velocity, v equals u plus at. So we are actually going to integrate u plus at with respect to time. And when I do that, I'm going to get s equals ut. Remember, u is just the initial speed, it's just a number. So we're going to have ut plus, and then t is going to become t squared. And then we will have to divide by that. And then we have our constant of integration as well. But we're going to use our piece of information we were given in the question that the initial displacement, so when t equals 0, the displacement is 0. So the displacement is 0 when t equals 0. So that means that 0 equals c, and we get our equation s equals ut plus a half at squared. So this shows you just another way of deriving 2 of the constant acceleration equations.